Hi. In this video, we're going to go through a few worked examples solving linear systems using augmented matrices, which is really essential in the cases that we're going to look at because they're fairly large, more complicated systems than some of the simple three equation, three unknown problems that we solved in the previous worked example video. So let's start with an example that's a big system. This is a system of 7 equations in 5 unknowns. Looks like a little bit of a beast. I promise you I've set this up so it is not overly difficult to solve, but it still looks like a bit of a mess. Trying to work through a problem like this using a system of equation form rather than using augmented matrix form ends up being very tedious as we keep writing x1, x2, x3, x4, x5, and so on. Right? So the simplification of notation that we get with augmented matrices is really essential for a system like this. I recommend that you pause the video, try to solve this system on your own. Then when you're ready, come back, resume the video, and follow along with the worked solution and compare that to your own work. The first step, of course, is going to be converting this into an augmented matrix form. How do we do this? Remember that to convert to an augmented matrix, really all we are doing is we're taking the coefficients of this entry only, including their sign, and putting them in the corresponding entries of a matrix with the right-hand side as the last column. Keep in mind that everywhere where there's a missing entry, we need to place a 0. Right? We don't need to fill these zeros in the system of equations form, but they are implicitly there, and when we move to augmented matrix form, we have to. Some people like to fill out augmented matrices column first. Some people like to do it row in a row-oriented way. It doesn't really matter. I'll walk through this column by column to highlight how this works. Okay? So how do we fill in the augmented matrix? The coefficients for x1 are 1, 0, 1, 0, 1, 0, 1. So we end up with a first column. I'll just highlight this. This first column, 1, 0, 1, 0, 1, 0, 1, becomes 1, 0, 1, 0, 1, 0, 1. We then move over to the second column. For the x2, the coefficients are 1, 1, 2, 1, 1, 0, 2, 1, 1, 2, 1, 1, 0, 2. Moving to the third column, negative 1, 0, negative 1, 1, negative 1, 0, negative 1, negative 1, 0, negative 1, 1, negative 1, 0, negative 1, and so on. The first 5 columns correspond to the coefficients in front of the 5 variables, and the last column corresponds to the right-hand side. Right? Fairly straightforward. The key things to remember are watch the signs and remember to put in the zeros for missing variables when we write it as an augmented matrix. Once we have everything in the augmented matrix, remember this has all of the information of the original system. We can translate back into this simply by writing x1s in front of all of the first column, x2s in front of everything in the second, x3s, x4s, x5s, adding them all together and putting an equal sign right, before the last column. Very straightforward. The rules of Gaussian elimination working with an augmented matrix are exactly the same also. We just don't have to carry around all of the extra baggage of writing out the variables and so on. I'm also here going to use the kind of the more compact form of highlighting what we're doing in the process of Gaussian elimination with this row operation notation. So Gaussian elimination starts the top row, leftmost entry. We want to use this as a pivot to eliminate all of the entries below, zero them out. 3 of them are already 0, so there's nothing to be done for that. So for rows 2, 4, and 6, we already have zeros, no work needed to be done. Right? We have to eliminate row 3, row 5, and row 7. All of these have coefficients of 1, so these can all be zeroed out by subtracting row 1. The 3 things we want to do then are subtract row 1 from row 3, row 5, and row 7, and take the result and put them back into 3, 5, and 7, respectively. Right? Working through that, we can start with the third row. 1 minus 1 is 0. 2 minus 1 is 1. Negative 1 minus 1, just to highlight here, same row. Negative 1 minus 1 is 0. 3 minus 2 is 1. Negative 3 minus negative 2 is negative 1. And negative 1 minus negative 2 is plus 1. Same thing then for row 5. 1 minus 1 is 0. 1 minus 1 is 0. Negative 1 minus 1 is 0. 3 minus 2 is 1. Negative 3 minus negative 2 is negative 1. Negative 3 minus negative 2, negative 1. Finally, the last row, 1 minus 1 is 0. 2 minus 1 is 1. Negative 1 minus 1 is 0. 3 minus 2 is 1. Negative 2 minus negative 2 is 0. And 4 minus negative 2 is 6. At this point, we have successfully eliminated everything except for the first entry. We're zeroed out everything except for the first entry from this first column, equivalent to isolating the first variable only in the first equation. We then shift our attention over a column and down a row, and now look at the next piece. Identify our pivot, a 1. We want to use this to eliminate all of the entries below. And again, 2 of them are already 0. So row 5 and 6, we don't have to do anything. We need to eliminate at row 3, 4, and 7. Once again, our coefficients are all exactly the same, so we subtract the second row from each of those. The 3 things we want to do: subtract row 2 from row 3, row 4, and row 7, and put them back in the corresponding rows. Right? Let's just walk through that process. For the third row, subtracting the first, putting the result into the third row. Here we actually see something interesting. These 2 rows are exactly the same. 1, 0, 1, negative 1, 1, which means when we do the subtraction, we get a row of all zeros. Remember, a row of all zeros in a augmented matrix is nothing to cause us to stop. It just tells us there's not very much information in that row. Moving down to the fourth row and filling in the corresponding one here. 1 minus 1 is 0. 1 minus 0 is 1. 0 minus 1 is negative 1. 0 minus negative 1 is positive 1. And 5 minus 1 is 4. We don't need to do anything for rows 5 and 6. We move down to the last row. 1 minus 1 is 0. 0 minus 0 is 0. 1 minus 1 is also 0. So 3 zeros. 0 minus negative 1 is 1. And 6 minus 1 is 5. We have, in this case, now successfully isolated another variable, successfully completed another pivot step. This entry is a 1, zeros all beneath, just as we did in the previous step, eliminating below. These two pivots have been taken care of. We move down to the next row and over a column. Here we hit a problem. We have a 0 here. Here we're going to do something slightly different. Here we have an entire row of zeros. Usually if we have a 0, we just look for the row beneath and swap the first non-zero and swap with this. When we have a row of all zeros, if we just make that single row swap, that's going to keep being a problem over and over again. Instead, what we do is we take this row of all zeros and we move it all the way back down to the bottom. You can actually devise a set of individual pairwise row exchanges that do this. It's just simpler to keep track of it by saying we're just going to move row 3 down to the bottom. And in doing so, all of these rows get shifted up 1 unit when we do that. Again, we're just reordering rows, but it's a little bit of an easier thing to do this than to do sort of a pairwise exchange. Right? So this, after doing this, we end up with our 0 down at the bottom. And these 4 rows are exactly the same as we had here. Right? This now sets us up to take our next step. So shifting our attention, just to recall where we were, we had already taken care of this position. We had already taken care of this position. And so we shift our attention over to the next piece. We look at this pivot entry, and in this case, we got really lucky. In this case, we already have zeros all out of the way, all underneath. There is no work to be done to eliminate the entries below, and so we then shift down and to the right again, putting our attention at this position. We want to use this variable as a pivot to eliminate below. Once again, 2 of the entries are already 0, so there's only 1 we need to worry about. Coefficients are the same. The operation we want to do is to subtract row 4. This is row 4 we're working at, from row 5, and replace that with row 5, and that will eliminate this entry. Okay. Doing so, just change the pen color so that it's a little bit easier to highlight what we're doing. We're looking at this row, row 5. This is where we're doing our replacements. This is what's going to change here. And once again, you notice that these two are exactly the same. Rows 4 and 5 are the same. 1, negative 1, negative 1. So when we do that subtraction, we end up with a row completely of zeros. How do we deal with rows of completely at 0? We've already seen these. The next step is going to be to take that 0 row and move it down to the bottom, and to take the rows above, so don't worry about this 0 piece, and shift them up. Right. Now what this gives us is our upper triangular or row echelon form for the matrix. Right. Just to confirm that this is indeed our row echelon form, we can walk through each of the pivots. We have a pivot, pivot, a pivot, a pivot, a pivot. We can tell they're pivots because they're the first non-zero entry in each row. And every one of them has been completely zeroed out beneath. This is what it is to be a row echelon or upper triangular form. We also note, remember that how do we classify the columns in a augmented matrix? The first 5 correspond to variables, and the last corresponds to our right-hand side or our constants. Every variable has a pivot. This means we have no free variables. We have no free variables. This tells us that this system will have a single unique solution. We already know that it has a solution of a single set of values, but we need back substitution to actually find what that is. So now let's carry on the process of back substitution using the augmented matrix form. We're not going to recast back into systems of equations until we've got our whole system essentially solved, until we've taken ourselves to a reduced row echelon form. With Gaussian elimination, we start with the bottom row, but we see it's all zeros. It's all zeros, so we move up a row to the next. The next one is also all zeros. We move up a row, look across, and find the first non-zero entry. This is the pivot that we want to use. And we want to use this to eliminate everything above. Right? Here we have a little bit of an easier case than in some situations, because we already have ones at all of the pivot values. There's no scaling we need to do. So here how do we eliminate these entries? We add or subtract the appropriate multiple of this 5th row from the corresponding rows above. To eliminate a -2, we add 2 times row 5. To eliminate this -1, we add row 5. To eliminate this +1, we subtract row 5. To eliminate this -1, we add row 5. In summary, these are the 4 operations. In each case, for row 1, 2, 3, and 4, we're going to add or subtract the appropriate multiple of row 5. Right? Walking through, I was jumping ahead, walking through actually what this does. Because of all of the zeros ahead of row 5, we don't have to worry about any of these first 4 columns. When we add or subtract a multiple of row 5, we're going to be adding or subtracting zeros. So this block of numbers remains completely unchanged. The only thing we worry about is these last 2 columns. So for the first, -2 plus 2 is 0. -2 plus 10 is 8. -1 plus 1 is 0. 1 plus 5 is 6. 1 minus 1 is 0. 4 minus 5 is -1. -1 plus 1 is 0. -1 plus 5 is 4. After doing this, we have successfully taken this pivot and zeroed out everything above it, as well as what we already had of zeroing out everything below and to the left. Now we've taken care of that one position. We shift our focus, so we've already dealt with this. We shift our focus up one row to the left one unit and take a look at this pivot. We want to use this to eliminate above. Right? Once again, we identify what we need to do by looking at the coefficients. To eliminate the 2, we need to subtract 2 times row 4. To eliminate the 1, we subtract row 4. To eliminate the -1, we add row 4. Each of the operations, we work on row 1, 2, or 3, adding or subtracting the appropriate multiple of row 4 to substitute again row 1, 2, or 3. As was the case in the previous example, we have all zeros here and a 0 here, which means in doing this subtraction, this block will become untouched. And this is also a 0, so this piece that was already all zeros will also stay untouched. The only things we actually need to work with are this column and the last column. 2 minus 2 is 0. 8 minus 8 is 0. 1 minus 1 is 0. 6 minus 4 is 2. -1 plus 1 is 0. -1 plus 4 is 3. After this step, we have now successfully eliminated the values above this position, as well as the positions below and to the left, just as we had already done here. So we now have 2 columns that have single values for pivots and everything else zeros. We are now ready to continue. We have already dealt with this position. We have already dealt with this position. We shift our attention up and to the left. The next pivot we want to eliminate upwards. Here we already have a 0, so we only have to do one thing. We'll add this 3rd row to the first, and that will eliminate that entry. As we have consistently seen, this row that we're adding has 2 zeros here. So this first block will be unchanged. It has zeros here, so this block will be unchanged. We only worry about the 3rd column and the last. -1 plus 1 is 0. 0 plus 3 is 3. The only 2 changes here. Here, because things are sort of getting simpler, I'm putting another operation on the same slide. After having done that, we have successfully zeroed out this column with the exception of this pivot. So we have all zeros, 0 to the left, same as we had in this position and in this position. So we move our attention up and over to the left. One more pivot to work with. How do we eliminate this? We subtract the 2nd row from the first. Right? This 2nd row also has a ton of zeros in it. There's a 0 here, and these are all zeros. So the only thing that we really think about are the 2nd column and the last. 1 minus 1 is 0. 3 minus 2 is 1. We now are in our reduced row canonical or row, reduced row echelon or row canonical form. Our pivot entries, of which there were 5 5 pivots. Every variable is a pivot, no free variables. Every one of these is in a column where it is the only non-zero entry. Everything else is 0. They all have a value of 1. This is what the reduced row echelon form means. The last column of this form directly contains the solutions. How is that? Well, we can see that by just sort of recasting to equation form and discovering that this form is a ridiculously simple equation. Remember, the first entries here correspond to the variables, x1, x2, x3, x4, and x5, and the last is the right-hand side. So how do we read this? The first equation reads x1 plus 0x2 plus 0x3 plus 0x4 plus 0x5, so we just ignore those, equals 1. The second reads 0 plus x2 plus 0, 0, 0 equals 2. The third, 0, 0, x3, 0, 0 equals 3. 0, 0, 0, x4, 0 equals 5. All zeros, x5 equals 5. These last two equations correspond to equations of 0, 0. They provide no information, but they're not problematic. They just don't add any extra information. The first 5 rows give us our answers. Right? We can either leave it in this form or write this out in vector form, the quintuple x1, x2, x3, x4, x5 equals the numbers in sequence, 1, 2, 3, 4, 5. This, even though it was contrived to have a lot of zeros to show up and to minimize the work, we still see that this was a fair bit of work to get to solve by hand in this very large system. But it would have been even more challenging, more frustrating to work with if we were trying to do that in a systems of equations form. Okay, just sort of recapping so that everything is in one page. How do we solve this system? There is a unique solution, 1, 2, 3, 4, 5. It would not be obvious, just looking at that we would have such a simple form. Okay. So let's move on to one more example. And this is a really interesting one that highlights another benefit or potential benefit of the augmented matrix form. Here I'm asking you to solve the same system with 2 different right-hand sides. If you look carefully, you will see that the coefficients on this equation, this system of equations, are exactly the same as the coefficients here. I'm telling you they are. I'm not. You can verify though if you wish. But the right-hand sides are different. Now, when we have a situation like this, when we have 2 different right-hand sides, but the same system, we do not have to actually do double the amount of work to solve these. Why? Because the rules of Gaussian elimination are exactly the same for these systems. Think about how Gaussian elimination works. We work through all with the variables. We start at the left-hand side. At the top equation, we work our way through down using the variable coefficients as pivots. We manipulate the last column, the right-hand side column, but that last column never dictates the rules, never dictates what manipulation we are going to do. What that means is if we had two systems with different right-hand sides, the manipulations we do applying Gaussian elimination should be exactly the same for those two. The numbers would just be different on the end. Augmented matrices give us a trick to solve these systems then at the same time. What we're going to do is we're going to actually create an augmented matrix that has one coefficient block, because the coefficients are the same, but two right-hand side columns. Right? Our process of going through Gaussian elimination is going to be exactly the same. Just remember that the last two columns are two different right-hand sides, as this will come back to, it will be important in interpretation of the results. Okay, so let's see what happens when we move through a system like this. First of all, how do we recast this problem in an augmented matrix with two right-hand sides? Well, the basic approach is going to be exactly the same. First of all, take a look at the coefficient piece. Either equation we can use because they're the same. Remember that blank spaces are zeros, and that when there's just a variable by itself, there's implicitly a 1 in front of those positions. And then fill out the corresponding first 4 columns, because there's 4 variables of this matrix. I'll do it column by column. 0, 2, 2, 4, 0, 2, 2, 4, 0, 1, 1, 2, 0, 1, 1, 2, 1, 0, 1, 1, 1, 0, 1, 1, and 1, 1, 2, 3, 1, 1, 2, 3. That is our variable block. That is our A matrix. Right? We then, in a normal problem, we'd only have one column. Here we have two different right-hand sides. So we fill in one column with the first right-hand side, 2, 3, 5, 8. And call this B1. This is B1. And then the last column, 3, 4, 7, 12, is our second right-hand side, our B2. Then proceed with Gaussian elimination. Standard approach. We start focusing our attention at the upper left corner. Here we see a 0. A 0 can't be used as a pivot, so we look below. We see there's a non-zero entry in the second row, so our first step is to swap rows so that we have a pivot in the right position. After we've done that, we have a pivot in the upper left. We can use this to eliminate below. We already have a 0 in the second row, so we don't have to do anything. To eliminate this 2 in row 3, we subtract row 1. To eliminate this 4 in row 4, we subtract double row 1. The operations are subtracting row 1 from row 3 and double row 1 from row 4 and putting them into the corresponding positions. Walking through that, row 3 minus row 1, 2 minus 2 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 2 minus 1 is 1, 5 minus 3 is 2, and 7 minus 4 is 3. For the fourth row, 4 minus 4 is 0, 2 minus 2 is 0, 1 minus 0 is 1, 3 minus 2 is 1, 8 minus 6 is 2, and 12 minus 8 is 4. All right. You might notice right away, there's something a little bit funny here. These these sort of 3 columns of 3, 4, and 5 are all the same for rows 2, 3, and 4, and we'll see what that is going to mean. At the time being, though, we will just carry on with Gaussian elimination. We used our uppermost leftmost position as a pivot. We now move down and to the right. We try to use this position for a pivot. It's a 0. We look below. Everything else is also a 0. What this tells us is that this position here is a free variable. There's no pivot in this second column. Right? Since we couldn't use this as a pivot, we don't move down a row. We just move over to the next entry and now move over a column and now look at this position. Can we use this as a pivot to eliminate below? Coefficients are all the same, so we simply subtract the second row from the third and the fourth. And this similarity here is going to lead to a lot of zeros. 1 minus 1 is 0, 1 minus 1 is 0, 2 minus 2 is 0, 3 minus 3 is 0. The third row becomes entirely 0. All right? The fourth row, 1 minus 1 is 0, 1 minus 1 is 0, 2 minus 2 is 0, but 4 minus 3 is 1, so we don't get a whole row of zeros. Right? Now, in interpreting the answer here, we have to be very careful. We have to keep in mind that we have 2 right-hand side columns. We have this kind of funny business. We have a 0 except for the last column. This should set off alarm bells of no solution, but we have 2 right-hand side columns. Let's think about this very carefully. Okay. Let's split this back into the 2 original matrices. Okay. So we were solving this together. I could have written this as 2 augmented matrices with an A block that's the same. This first block is A. And all I've done here is taken this B1 column and put it there. And this one goes over here. Separate this out into 2 standard augmented matrices with just a single column. And now let's take a look at these 2. These 2 different matrices give us different interpretations. In the first one, we have 2 rows of all zeros. That's totally fine. There's nothing wrong with rows of all zeros. We have a pivot in this position. We have a pivot in this position. So x1 and x3 are pivots. We also have a free variable in this position and a free variable in this position. Our analysis of this row echelon form says the first system will have multiple solutions. We need back substitution to solve it. The second system, on the other hand, has this row of all zeros except for the last column. This corresponds to a 0 equals 1, an inconsistency. The second system has no solution. This is something we're going to get at further on down the road. It is absolutely possible for different right-hand sides to change the nature of the solutions. In particular, a system can have no solutions for some right-hand sides, while it has solutions for other right-hand sides. Okay. Since we've already identified that one system has no solution, the only thing we need to do for moving forward is focus our attention only on the first system. We no longer need to have 2 columns. we will only work with this second, so this middle matrix here moving forward. So that matrix for the first system, augmented matrix for the first system, already converted into row echelon form. Now we work with back substitution. Remember, back substitution, we start at the bottom. Bottom row, all zeros, so we move up. Second to bottom row, all zeros, so we move up. First non-zero row from the bottom, we identify the pivot, and we want to use that to eliminate above. But look, we're lucky. This already had only a single entry and all zeros above. There's nothing for us to do. That means we shift up another row, look at the pivot. Remember, we only use pivots in this isolation piece. The pivot is the first entry, so that's this position. This is the upper corner. We don't need to eliminate anything, but we do want to scale this so that we have coefficients of 1 everywhere. We divide this first row through by 1, so 2, 1, 0, 1/3 becomes 1, 1/2, 0, 1/2, and 3/2. This is now a matrix in reduced row echelon form. We have a pivot with all zeros, a pivot with otherwise all zeros. Both have a value of 1. Right. Remember, this is our right-hand side column. The first 4 blocks of our variables. Pivot, pivot. That means that these 2 other columns are both free variables. This is something I don't think that we've seen before in the examples. 2 free variables. Whether we have 1 free variable, 2 free variables, 10 free variables in a larger system, doesn't change the basic approach. We solve for the pivots in terms of these, and when we are in a reduced row echelon form, that solution will be very easy. We recast from the reduced row echelon into equation form. What does this first row read? This first row reads x1 plus half x2 plus 0x3, so nothing, plus half x4 equals 3/2. Right? We know that x2 and x4 are free variables, so the only thing for us to do is to move those over, and this gives us x1 is 3/2 minus half x2 minus half x4. Second to last equation, or the second equation, reads as 0, so nothing in the x1 position, but 0, nothing in the x2 position, 1 times x3 plus 1 times x4 equals 0. Again, x4 is a free variable, so in order we express x3 in terms of that, x3 equals 2 minus x4. We're basically done. We have here expressed our 2 pivot variables in terms of our free variables. What can our free variables be? x2 and x4, our free variables, can take on any number. No matter what we put as x2 and x4, we can come up with an x1, x3 that will make this system satisfied. Again, we often recast this in a parametric form. To do this, we simply substitute new symbols for both x2 and x4. Here I'm using S for x2 and T for x4. And so that would simply mean that the x2 here becomes an S, the x4s become T's, and we would write our final answer as the vector x1, x2, x3, x4 equals 3/2 minus half s minus half t for the x1, s for x2, 2 minus t for x3, and t for x4, where those values can take on any possible value. Right? In summary, this system with two right-hand sides has two very different results. Right-hand side 2 has no solution. It's an inconsistent system, whereas right-hand side 1 has multiple solutions that we can write in parametric form. Right. So we've gone through two fairly involved problems, large problems, where we can see the power of the augmented matrix form in simplifying the notation so that we can work with big systems, in providing a mechanism that we can work with two right hands at the same time, and so on. In general, I find that working with the augmented matrix for essentially any problem I'm trying to solve by hand makes things much easier. And so hopefully this has given some extra practice with that. There will be one more set of worked examples for this unit where we work through using Gaussian elimination to solve so-called real-world problems where we're not simply presented with a system, but we actually need to formulate the system, use Gaussian elimination to solve it, and then interpret our mathematical result in the context of the problem. Thank you, and goodbye.